Well, welcome everyone to another lecture in the IFAS AI seminar series. Our guest today is Dr. Manoj Karkee. He's a professor and director at the Center for Precision and Automated Agricultural Systems and the Biological Systems Engineering Department at Washington State University. He received his PhD in agricultural engineering and human-computer interaction from Iowa State University. He has published widely in journals such as Computers and Electronics in Agriculture, Computers in Industry, the journal Field Robotics, and has been an invited guest speaker at numerous national and international conferences and universities. Dr. Karkee is currently serving as the editor-in-chief for Computers and Electronics in Agriculture and associate editor of the Journal of the ASAB. He's also an elected chair of the International Commission of Agricultural and Biosystems Engineering, Section 3, Plant Production. So please welcome Dr. Karkee.
Thank you very much, Dr. Marioris, and thank you everybody, and particularly for giving me this opportunity to come and share some of the thoughts around AI and robotics, specifically to when it in relation to specialty crops. My research focus in the last 10-12 years has been in that area. So I'll again be happy to share some of the thoughts I have and some of the work I do in this space. So with that, I would like to share my slides here, and then we'll go from there. Do you see my presenters mode or the full screen view?
Yes, we see it correctly.
Okay, great. So I wanted to start with some historical thoughts around the evolution of agriculture before we jump into AI and robotics and how it plays its role in moving to agriculture 4.0 and smarter digital farming era or beyond that. So we go back 100 years ago, or more relevantly, I would say in some part of the world, it is still happening, where we use hand tools and animals to perform various kinds of field operations in agriculture, whether that be for plowing fields or planting or weeding or whatever else we need to do to grow crops or animals. So certainly in many parts of the world, it was done long time ago, and the farming was done that way a long time ago, at least in row crops such as corn and soybean. But in many other parts of the world, such as my native country, Nepal, or some countries in Africa and Asia, the planting of various kinds of crops is still done that way. And then when fuel and engines and hydraulics started to play a role in the industrialization, agriculture also got benefited by the development of mechanization tools, and that led to farming or agriculture 2.0. In this kind of farming, we do field management or crop management at field level, often uniform operations, such as applying nutrients uniformly over a given field, treating all animals equally for their intake or anything else in terms of management. And then when sensors, computation, communication infrastructure, and positioning tools such as GPS or Global Navigation Satellite System, GNSS, started to again impact the society around the world, agriculture also got benefited by those empowering or enabling technologies, and it started to make these machines more automated and intelligent. And we started also develop robots to perform a few farming operations. Now we are getting down to a smaller block or parcel of fields in terms of managing crops and animals. We are trying to optimize input to, again, smaller field areas and individual or a small group of animals. And that is, I think, what we refer to as agriculture 3.0. And then recently, with the advancement of artificial intelligence and computing technologies and other enabling technologies, we've been making our farming operation, or at least trying to make our farming operations even more intelligent, more smart, trying to not only help with decision making in terms of what kind of input is necessary and when and where, but also developing robotic solutions that would implement those decisions, which is, I think, in general, what we term as agriculture 4.0 or smart farming kind of technologies. This agriculture 4.0, I think our goal has been and will continue to be advancing technologies for plant level management and understand and manage needs of individual trees and animals, such that we can maximize the quality and output or the yield from these farming systems, while also minimizing or optimizing at least the inputs that need to be provided to these agricultural farming systems, including optimization of labor use. Here is an example of how Ag 1.0 would occur, and is still occurring in various parts of the world. And as we got into more mechanization, developing large scale equipment for plowing and planting and chemical application and harvesting, again, we kind of started to use these big machines, reducing the use of manual labor dramatically. If we have to put a number, I think in US we went down from about 98% human or populations involved in farming to about 1 to 2% now. And then as we got into more automation and robotics and Ag 3.0, we started to see these weeding robots, auto guidance being implemented in most of these tractors around the world. So again, things are getting into that automated and autonomous operations, as well as intelligent decision making. Putting this all together, I think we started with mechanization, added automation and robotics, and we started to look into the needs of individual plants or the needs of a group of plants in small areas, and same thing with animal farming. And interacting among those components, we got into the current generation, or at least that's where we were trying to go. I believe in most part is the agriculture 4.0 or smart farming. With that concept behind, I would like to spend a few minutes around how artificial intelligence is playing and is going to play even more integrated and impactful role in the future in all of these farming activities we do in different kinds of farming environments. So on our left is the foundational models that artificial intelligence provides, such as machine learning, including deep learning techniques and models, expert systems and heuristics, predictive modeling, all these, again, foundational algorithms and models, generative AI and the one of the latest advancements would also be a part of that foundational models or tools that are provided to us. And then these AI algorithms and models would then enable us to develop and advance various kinds of technologies, such as pattern recognition, machine vision, big data analytics, robotics. And so all those technologies that then enable us to understand the various aspects of farming and then make decisions that would and implement those decisions actually that would help minimize or optimize inputs while ensuring desired quality and yield of the crops and our animals would be achieved. Where does it help in terms of our agricultural operations? Pretty much everything we've been doing or we need to do in producing crops and animals or other agricultural industries. Water and nutrient management, for example, pest management, canopy management, harvest and post-harvest operations, all those things have been and will continue to be positively impacted by this interaction and between AI and cyber physical systems, but also because of these enabling technologies that we have been seeing advanced very rapidly in recent years because of the enabling AI technologies that are coming out of various research and development programs around the world. This kind of interaction between, again, artificial intelligence and in the technologies that are enabled by AI would help us achieve the ideal precision ag goal that we all, I think, are striving to achieve, which is to understand and manage the needs of individual plants and then achieve, again, the maximum potential of individual plants and animals that we are managing. With that kind of quick background behind, I would like to focus a little bit more on automation and robotics and how AI plays a role in these technologies and why we would like to advance these technologies and implement and adopt those technologies in farming. So in the next several slides, I'll be talking about the challenges, the opportunities, the efforts that is going on around the world, and also a few examples from my own research program in these specific aspects. So to begin with, automation and robotics has a huge role to play in various kinds of farming operations. I think certainly focusing on specialty crops, particularly fruit crops and vegetable crops here, but it would be true for many other farming farming industries, including animal farming industries, where automation and robotics is essential for a couple of things. One, to minimize the dependence on depleting labor force, and that is being used for farming, particularly in these specialty crops, where most of the operations such as harvesting, pruning, thinning, pollination, not pollination as much, and some logistical operations are performed manually. This not only, again, requires a huge amount of seasonal labor to be used in farming, which is not sustainable, but also poses worker health and safety issues. As we can see here in these pictures, exposure of individuals in field environment where toxic chemicals are being applied, that's one challenge. This is also exposing workers to potential ladder fall and accidents associated with using ladders in various ways. It also exposes workers to injuries caused by repetitive motion. Also exposes workers to harsh field conditions such as hot summer days and cold winter days. So I think all those workers' health and safety issues, as well as the demand for our large volume of seasonal workers, are something we need to address, and I think automation and robotics plays a huge role there. There has been long research and development in this area. However, only limited commercial adoption, particularly in, again, specialty crops such as fruit and vegetables. There are a few limitations, I think, in my opinion, that is causing us to not be able to adopt most of these technologies in a broader commercial operations. One of them is accuracy and robustness, or their lack of desired accuracy and robustness of these automated robotic machines, such that it makes commercial sense or practical sense for farmers to adopt. The speed of various kinds of robotic machines are still pretty slow, and that again also compounded with the complexity and cost and accuracy, or the lack of accuracy and robustness. It makes it difficult to justify commercial adoption of these advanced robotic automated machines that we have been developing. So I think these are some of the major challenges. Certainly, there are socioeconomic challenges of rural communities and various other factors, policies and rules and regulations. But I'm just focusing mostly on the technological side today. To address these limitations and accelerate adoption of robotic technologies, researchers and technology companies around the world are putting a lot of efforts into primarily two sectors of robotics, or two components of robotics as it relates to specialty crops. The first one is what we call navigational robotics, where we develop and advanced technologies for understanding the environment, developing algorithms to efficiently plan the paths that robots could take to go around and perform whatever operations they need to perform. This has been an area of, I think, the most efforts and advancements, and to some extent commercial adoption in the past. Some example would be companies such as Actonomy and Burrow coming up with platforms or aid-on toolkits that allow existing machines to be autonomously operated in various kinds of fields, such as orchards and vineyards. And then another aspect of robotics, manipulative robotics, where we use manipulators and effectors to perform various kinds of field operations, such as pruning and harvesting and thinning and weeding. I think this is an area of active research and advancement in the last decade or so. We're making a lot of progresses there, but I think it is still, in terms of commercial adoption, we're still lacking behind compared to navigational robotics. Let's talk a little bit more about navigational robotics when it relates to various kinds of cropping systems, with particular emphasis again in specialty crops. There have been a lot of efforts in this area, as I mentioned earlier, in the 90s and early 2000s, when researchers developed auto guidance and self-steering systems for tractors using primarily GPS-based localization. There were some research and development in Bayesian-based guidance as well, but I think practical adoption was mostly around using RTK GPS, real-time kinematic GPS system for localization, navigation, and then using auto-steering technologies to drive tractors in straight lines, following predefined rows of crops and things like that. In recent years, however, there have been a lot of efforts from various research and research programs and technology companies around the world in developing autonomous or automated driving and navigation systems for various kinds of robotic platforms, small and big, and to perform a wide range of field operations, such as weeding and chemical application. These examples here are from our research program at WSU. One on our top left is something we developed about a decade ago now, I would think, for robotic weeding. And the one to our right is a robot we designed for managing or handling full beans of apples that would be laid in the orchards after harvesting. As I mentioned earlier, there have been a lot of technology companies coming to this space and commercializing or trying to commercialize autonomous driving systems for various kinds of vehicles. Autonomy with GPS and vision system working together has been, I think, the direction in recent years, and it has been enabled by deep learning and other advancement in the AI technologies, as well as the computational and connectivity or Internet of Things technologies that have enabled these efforts in recent years. And it has been companies such as Svanto and Blue White and Ectonomy coming up with, as I mentioned earlier, toolkits that we could aid onto our existing tractors or other ground vehicles to make them automate, to enable automated driving or autonomous driving in some cases. And standalone machines such as those from John Deere, Gauss, and Monarch are also making their ways into farming. Some successful examples of these autonomous or automated navigational robots include smart spraying. For example, this robot from a robotic sprayer from Robotics Plus and Gauss, they can go around and spray chemicals without having a driver on board, mostly autonomously, but I think there are still some situations where operators have to remotely control them. Weeding, for example, carbon robotics machines are going through the fields automatically with autonomous driving capabilities to detect and apply laser lights to kill weeds. Logistics of agricultural products or produces, such as the robots from Burro, are being used. The one in the middle here are being used to move various kinds of fruits after they're harvested by human or otherwise in the field to loading stations. In that mix, we recently developed a robot and submitted this into a competition called Farm Robotics Challenge, organized by University of California A&R, Agricultural and Natural Resource Sciences, I think, a unit there. UC A&R, they organized this competition called Farm Robotics Challenge, and we submitted this this prototype robot, and we were awarded I think one small farm award or something like that. Our team was pretty happy about it. But anyway, I wanted to show a quick video of our latest effort around navigational robotics. So as I mentioned earlier, we are using GPS and vision-based inputs to improve the reliability of these navigational robots. This robot has capability to detect various kinds of obstacles, including human, and maneuver around those. Let's get into manipulative robotics a little bit. There have been a lot of research programs around the world developing robotic systems for various kinds of manipulative operations in specialty crops, such as picking fruit and vegetable, pruning and thinning. Here are example research programs from various parts of the world. By no means this is a comprehensive list, but I just wanted to give some examples of the research programs that are putting efforts in developing robotic harvesting. This has been and is currently still one of the most active area of research and advancement in terms of manipulative robotics in specialty crops. That's also reasonable because harvesting is the single most important operation in terms of labor use and worker health and safety, and that's why we're putting a lot of efforts in this area to automate fruit picking operations. There are also private companies such as, there are specific research programs such as this one in Europe. I think it is now ended maybe recently. Clever robots for crops and sweeper. These are two projects carried out in Europe over the last decade or so. And this company out of out of New Zealand, Robotics Plus, has put a lot of effort in developing and advancing robotic picking solutions, particularly emphasizing kiwi and apples. Harvest Crew, many of you perhaps are familiar with this because this comes out of Florida, and they have put really targeted effort in picking strawberries. Another company out of Israel called FF Robotics, and they're putting their really focused efforts on picking apples, and they're testing it in various parts of the world. Advanced Farms out of California is putting efforts in strawberries and apples. And Tevel, a company out of Israel, has been using flying robot or drones to perform robotic picking operations of apples and other kinds of fruit crops. In addition to harvesting, as I mentioned earlier, we've been putting various efforts both in the research programs as well as in private companies to automate other farming operations in specialty crops, particularly around canopy and crop load management. These, again, example programs here are just to give you a quick sense of where things are happening. By no means, again, it is a comprehensive list. In this mix, WSU Egg Robotics program that I lead has also put a lot of efforts in advancing automated and robotic solutions for specialty crops. We emphasize a few specific areas in our research program. Particularly, we focus on developing human-machine plant interaction systems and understanding, such as the study of fruit tree dynamics, understanding manual operations, such as the forces and motion necessary in picking apples. We also focus on optimizing vision systems for orchard and other specialty crop applications, such as utilizing artificial lighting when necessary, optimizing various kinds of AI models, such as variants of convolutional neural networks, assessing light intensity variation with changing leaf angles as we understand the reflectance coming out of an object depends on so many factors, particularly in crop canopies. How the leaves are oriented would make a whole lot of difference, and we would like to understand how light intensity varies with changing leaf angles and how we could utilize that in our modeling. Differentiating hard versus soft obstacles so that robots could pass through, for example, leaves to reach fruit and grab them and pick them, versus they could avoid hard obstacles such as trellis wires and branches and avoid colliding with those. Generative AI for label dataset generation has been our recent effort around utilizing advanced tools in developing various kinds of machine vision systems. Innovative manipulators and effectors for various field operations has been another area of our focus. For example, we've developed and tested various kinds of end effectors for fruit picking and flower thinning. Been using mechanical, pneumatic, and water jet and some other techniques to perform these operations. Certainly been learning a lot in terms of what works and what does not work, but we're trying various kinds of potential techniques to perform field operations. Here is an example of our effort. On our left, this video shows the progression of apple picking robot in our lab over the last 10 years or so. And on our right, this is a robot developed by Fresh Fruit Robotics in partnership with our program. This robot has 6 arms on the left side and 6 on the right side. Altogether 12 arms operating simultaneously. And been tested in Israel and Washington State in recent years. We've also developed robotic solutions for flower thinning, as we can see in this specific video. We've also developed robotic solutions for pollinating fruit crop flowers, as you can see here. Among other things, we have also developed a robotic system for fruitlet thinning in orchards. A quick demonstration here. To summarize, we've been developing various kinds of robotic solutions for fruit crops, particularly for apples and cherries. We've learned that the recent advancement in AI models, particularly deep learning models, have enabled us to perform these vision tasks in orchard much better and much more robustly compared to 10 years ago when we were using more conventional machine vision systems. Certainly, we are optimizing these models various ways, as I mentioned earlier, to make them even better for our specific applications. In case of robotic harvesting, been achieving up to 80% peaking success rate with about 5-second cycle time, which is the time taken to pick one fruit on average. Robotic pruning of UFO cherries has shown that we could achieve about 60% success rate, and the cycle time is like 35 seconds. There's a lot of room for improvement there. Robotic thinning, we were able to remove about 62% of flowers that we targeted with a cycle time of about 7 seconds. Robotic pollination has been something we've been feeling really good about. We can pollinate up to 85% of flowers, and we could do that in about 4 seconds. We have also adopted some newer advancement in this particular technology, and we envision being even more efficient and faster compared to these results. And then robotic pollination also allows us to place fruit in target locations that we want them to be at, which minimizes the clusters of fruit, position themselves as that the light interception is better, position themselves as that the robotic harvesting is easier because now we can access each individual fruit with a robotic picking system. So robotic pollination, in my opinion, has a lot of opportunities to revolutionize fruit farming, and so we are putting a lot of efforts to potentially commercialize that technology. So with these two component technologies discussed a little bit, in the next couple of slides, I'd like to discuss how these two kind of components of robotics are coming together into autonomous farming. We've already seen various kinds of technologies, including both the navigational robotics and manipulative robotics integrated together to perform various field operations, and also allowing them to work together in a group of robots called also Swarm Robotics. This company called Swarm Field Robotics from Australia have been working in this area for quite some time, and they have a couple of different kinds of robotic systems available for farming. They work collaboratively in autonomous modes. these technologies are capable of row following and headline turning. They have remote monitoring and intervention capabilities. They often detect and avoid obstacles, and they have emergency stoppage when necessary. They have also been used for a few specific field operations, such as weeding, mowing, thinning, and chemical application without direct human intervention. And ongoing research in this space include nutrient application, harvesting, pruning with these integrated machines that can, again, drive by themselves, get to the field, get to the target areas, and perform whatever operation need to be performed autonomously. Here's a quick example from my research program on automatically making a decision in terms of how much nitrogen would be necessary for individual trees, and then driving through the orchard rows to get to those target trees and apply right amount of nitrogen at right time. We've been using some historical data to make the decision in terms of how much nitrogen would be necessary. That includes understanding the canopy growth during summer months, understanding how leaf color would change during late fall, estimating trunk diameter, and various other parameters such that we make more efficient and robust and reliable decision in terms of how much nitrogen would be necessary. That information is stored in a database, which would be then pulled during the field operation for specifically when we're applying the nutrients. And then a model would be run based on the historical data, historical parameters that we have stored, as well as the real-time information that the sensor would be able to capture, such as the trunk diameter for a tree that we are currently going to apply the nitrogen to. We've also been working with our collaborators in Florida and California to develop a co-robotic system for strawberry harvesting. Also, again, includes navigational and manipulative robotics, so that these robots could go work in a group by themselves with as little human intervention as possible. As we move into the future, I think there are a few very specific areas that I think we need to continue to work on, both in the research and development programs, public research and development programs, as well as private technology companies. Total autonomy. I think currently we're trying to develop automated or autonomous solution for one or two specific operations in the field. But then for practical commercial adoption, it doesn't always lead to logistical and economic benefit that that growers would like to have. For example, if we are using a autonomous spraying system that goes down the rows and apply whatever chemical it needs to apply, but then if workers have to be there to fill the tank of this robotic chemical applicator, farmers are not as excited because they still have to have somebody attending the machine to supply that chemical it needs to carry and apply to the plants. So another example would be we're focusing a lot in harvesting apples, but farmers are still hiring a lot of people to prune and thin and apply chemicals in different times over the growing season. Automatic harvesting is good, but it is not enough for farmers to be as excited and be able to alter the way they do farming. And that's why advancing all kinds of automated robotic solutions to perform almost everything that happens in these specialty crops would be the direction for the future. Robustness and reliability. A lot of these solutions still need substantial improvement in terms of their robustness and reliability. As I mentioned earlier, I have tested a few robots that are out there, and my own robot, they often stop in front of a tall grass, and that is something safe to pass through. Same thing with picking fruit. My robotic hand would not push through leaves to grab a fruit that is behind those leaves, which is safe to do, versus sometimes it is not safe to pass through obstacles when they're going to cause damages to the robot. Capability for AI VR-based operation, this is nothing new in terms of the technology, but I think we can implement remote operations and maintenance and supervision of autonomous agricultural machines using augmented reality and virtual reality solutions. Plant level management, I emphasized that a little bit already. I think moving forward in the future, we would like to develop an advanced solutions that would understand the needs of individual plants and manage those plants in terms of what kind of input, such as water and nutrient and the chemical would be necessary, and also evaluate how that individual plant level management impacted the end results in terms of the yield and quality of fruit, for example, if we are talking about fruit crops. Enable current way or disrupt with new philosophy of farming. This is something really interesting. I think we all have to ponder upon. I think with smaller robotic machines, AI-enabled solutions such as self-invest applications, we have the capability now or the opportunity now to continue the way we farm our crops and animals, or start looking into a different kind of farming where we kind of have let's say in terms of monoculture, we have diversity of crops and animals. We are co-locating them. In any way, we can change the way of farming. There is this opportunity with the modular robotic and AI solutions. And finally, attracting new generation of farmers into farming is very, very important. As we all know, farmers around the world are aging, and there has been lack of interest in the younger generation to get into farming. I think with AI and autonomous and automated and robotic solutions, we have this opportunity to engage and attract new generation of farmers as well as the students and researchers into agricultural domains. With that, thank you very much. If you need more information about my research program and the center I lead, and here are the QR codes. I don't know if it is possible to scan them right now, but the video would be posted, and the potential the slides would be available as well, just in case you'd like to connect back. With that, thank you very much, and I'll be more than happy to take any questions and have more conversation.
Thank you very much for a wonderful talk, Dr. Karkee. So I'm sure we must have some questions from the audience. Looks like Rafa have a question.
Let me ask a quick question. This is Rafa Muñoz Carpena. I'm a professor here at the Agriculture and Biological Engineering Department. So you rightly pointed out the challenges of realizing Agriculture 4.0, which is autonomous machines. I mean, the whole idea has been always about, can we make autonomous machines that can do tasks that humans could do, or even better than humans, okay? And the challenges, we have seen that on the self-driving vehicles, you know, and all these things. How far do you think we are from really overcoming these main barriers, both on the back end, the front end, the mobility, the algorithmically even speaking? I mean, where are we right now? Because this seems to be a moving target. I mean, we were promised that self-driving vehicles were going to be here now, okay? We are now delaying them, I don't know when, okay? And so in your opinion, as an expert, what are those?
Thanks a lot. Let me start by saying that farming environment offers both the opportunities and challenges for autonomous operations. And I tend to think that eventually it will be easier to have an autonomous machine in farming than on the roads, because we are not as close to the obstacles, that dynamic set of obstacles that are present on the roads. I totally understand, and I have been looking forward to autonomous driving myself, and it has been a really quickly moving target. When it comes to agricultural applications, we can often constrain the environment and create an environment such that I think autonomous driving, in my opinion, would become reality sooner than later, sooner than we think. Actually, it is already happening to some extent. We have machines such as GOS and Robotics Plus. They go through orchards, turn around, and find if there are any obstacles, stop if needed. Particularly in crops with good structure, whether that be row crops with lines of crops that are pretty easily identifiable, or apple orchards or grape vineyards where trees are permanent and they're always there. They have a given structure. I think these autonomous machines have easier way getting through them and then operate the way we would like them to operate. However, they also often are faced with challenges that are slightly different than what we see on the streets, because we don't have marking, we don't have defined areas where these would be allowed to operate versus unsafe areas. We have to make our intelligent decisions in terms of path planning and making sure it is not, for example, too weight or the details are not too deep. I mean, there are a lot of other challenges where we need to make intelligent decisions that would be more difficult than in self-driving cars, I would think. I think to summarize, I think we're getting there, and I think we'll see autonomous driving in agriculture, are already seeing some of that, and we'll see more of those in recent future.
So I was going to ask it, because so far, even if we got to autonomous, we are still focusing on single task machines, where a farmer, when they walk their fields, they're doing several things at the same time. They're gathering information from what's come next. They could even stop and fix something. They could be doing on the side while they are there something else. And essentially, is there a vision that these autonomous solutions will be able to be multitasking and also prioritize? Because one of the problems is, if you give them several tasks, what's the priority? How do they, in an efficient way, realize those? So is that kind of higher level in the picture right now, or is we are only focused right now on having the one robot that moves around and moves the fruit back into the pick, and into the classification area, or whatever that we have seen examples of?
That's a good question. I think we're currently focusing on individual tasks as the research and development, but I also emphasize that we need to start looking into multitasking. Multitasking in two sense. One, same robot that could do one thing at a time, and then let's say two months later, when there is another task to be performed, that same robot could do that. And that's one way to look at it. Another, as you mentioned, when farmers are driving a tractor, they're harvesting corn, they're making sure the corn is being delivered to the grain cart without dropping them on the ground. They might be at the same time looking into, is the field too weight, or is there something else that need to be considered before continuing the farming operation, or in this case, harvesting? So there are simultaneous things that are happening that individual operators are looking at. So multitasking at a given moment would be one aspect, and multitasking staggered over time would be another aspect. I think robots have that capability to do both if we design them with that purpose in mind, but we're not perhaps putting as much effort right now. I think, for example, we're always focused on either doing harvesting or pruning or thinning, and designing our robots for that specific operations without looking into how it could be designed so that it could do multiple things when needed.
Thank you.
I'll potentially stop there, but I think there is always that opportunity to aid that kind of intelligence once we have the solutions that are pretty robust for individual operations.
Thanks.
So I'd like to pick up on that question, if I might. I found a very interesting comment, a very interesting discussion, because of course I certainly agree that we've been focusing on, developing specialized operations just really to limit the scope of the work and address something that can be done. But while you were both talking about that, I was thinking that we know that there's a lot to be gained in terms of AI model from like training multitask models, right? We've seen a lot of great breakthroughs by doing that. So do you think that we might be missing on an opportunity by not looking at multitask platforms while we develop the models?
I think we should start looking into that direction. I think I emphasized that in one of my last slides there. I think it was reasonable to begin with individual tasks when we're learning and understanding whether we could do any robotic operations in specialty crops, and whether we could do autonomous row following, for example. I think it was reasonable to begin there, but I think we have now advanced these technologies to the level that we need to start looking into multitasking and multiple operations, and start thinking about the design that would incorporate those aspects as we move forward.
Do we have more questions from the audience?
I have a question.
Please go ahead.
Hello, Dr. Karkee. It's Kevin Wong from UFGC Gulf Coast REC. Thank you for your presentation. Very nice research. So I have one question about your the one comment on your last slide. You mentioned the VR and AR applications, robotic applications. You said that the connection is hard. So I wonder, like, have you, like, maybe, I don't know if you can present that, like any like AR and VR applications you leverage for your robot development currently, and can you explain like why you think it's like there may be some bottleneck or like obstacles with AR and VR and robotic, I mean real world application? Thank you.
Thanks. I think as we start to look into this multi-purpose robotic machines operating in the field, supervising, monitoring, and when needed, operating remotely becomes a huge component of this farming system of the future. And that certainly then brings up this concept of, I mean, we could have simple remote operation, but I think having a realistic AR, VR environment to supervise, monitor, and operate when necessary, I think would be reasonable, in my opinion, a logical next step. The technology exists, as we all know. We fly internationally from a location in Phoenix, for example, and we are doing that kind of work 20 years ago when I was doing my PhD to drive tractors using AR, VR capabilities for various kinds of testing. But I think it hasn't gotten into mainstream development and implementation. One reason, as I mentioned, is the connectivity. Other, certainly, we still are focusing on advancing automated solutions and make sure they work. But again, as we head into the future and as these machines make their ways into farming, I think AR/VR capability to monitor, supervise would be essential. Specifically about my research program, I was recently funded by Cyber Physical Systems program to develop AR/VR solution for monitoring robots in apple orchards. I don't have any solution in place yet, but we are working towards that.
Thank you. Thank you.
Like we have a question in the chat from Dr. Charlie Lee. He's asking, how do you see the role of academic researchers in developing ag robotic solutions, while industry seems to have more resources and be moving pretty fast?
Very, very good question, Dr. Lee. This has been and continues to be an interesting and often a pretty critical challenge that we academic researchers are facing. Every time submit a proposal to our funding agency, there is always a comment back, well, such and such companies are already working on it, or there is a solution already exists. Why do you need to work in that area? I think we need to start creating a collaborative environment where we openly share what their capabilities are, what our direction is, what exactly we're working on, and then identify pieces that would complement the efforts of each other so that we continue to advance and accelerate the development and adoption of these technologies. I mean, honestly, companies are focused on one specific thing based on what they know at the moment, and certainly their research and their development life cycle is really fast, but they're not looking into other complementary aspects that would enable them to be more robust and add more capabilities, more functionalities when they are successful in that one specific focus area they're currently working on. I mean, I have found that pretty regularly. For example, when I was working with FF Robotics, they're so focused on harvesting, but they're also interested in implementing pruning and thinning. If we had that solution ready for them, once they were pretty confident about their solution on harvesting, I think we need to start collaborating with them more closely. We might be doing already in our individual research programs, but I think we need to have wider, larger efforts in bringing researchers, technology company developers, and leaders, as well as farmers together, so that we understand where we all are, or what we're working on, and where we could play a role, so that this is a complementary, collaborative effort and not a competitive effort.
All right, so well, we're at time actually already. So if you could, Dr.
No worries.
Karkee. Well, so I'm sure we could continue this conversation the whole day, I'm sure. And I'm sure Dr. Karkee will be more than happy to communicate with everyone here. Know that there's a lot of interest in his work and a lot of potential synergies with what we're doing. So I'd like to thank Dr. Karkee again for his time, and thanks everyone.
Thanks a lot. Again, appreciate the time and opportunity to share some of my thoughts here. And this great group of researchers. See you again in some venues, and hope to be in touch.
Thank you.
Thank you. Bye-bye.